Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we've been looking at some basic concepts with respect to computer architecture. So, we will continue on some of the basic concepts and learn more as we go by. So, a quick review of some of the basic concepts that we have been looking at before we proceed further in today's lecture. Remember this big picture that we have been talking about, which is called as the von Neumann model. So, we have the processor as the central piece here, and then we have the input interface, we have the output interface, and the input, the output and the interfaces for both these, and then you have the memory and storage. And under the von Neumann model, these basic 4 units are the major functional units that we need to understand. So, we need to look at details of what happens inside the processor, what happens inside the memory storage unit, what happens for the input and the output operations. We will just zoom in a little and look at a little bit more of details inside a PC. So, let us look at this picture here. Again, you can see that this is our CPU box that we saw earlier, which has CPU. It also has cache, which is actually part of the memory structure, which is there inside your microprocessor. And then there is a bus interface unit, which serves as the as some kind of an interface. Okay, and then you have the main memory here. Then you will have the system bus, which acts as an interface which connects up the main memory, the processor and the different other input and output blocks that we have here. So, if you look at this here, we have what is called as a peripheral I/O or interface control unit here, and then you have the hard disk control, which is the interface for the secondary memory. Similarly, you will have a video controller which will act as the interface for the video monitor. You have the keyboard control which acts as the interface for the keyboard, and then the network controller which acts as the interface for the communication network. Similarly, you have other I/O expansion slots that are normally provided on your PC, to which we connect different I/O devices as we come across. Okay. So, you can see that again basically it is the same processor, memory, input output that we have. Only thing is this inside view gives you how they are actually interconnected. Okay. So, you will find that there are a lot of interconnection that we have, and then these different units which are connected amongst one another. Okay. So, this is what we call as an insider's view. Okay. So, now the operations in a computer, this is also something that we have looked at earlier. So, just again a very quick recap of what is there, what is happening inside a computer. Now, we know that activity in a computer is governed by instructions. That is our first statement that we are talking about over here. Activity in a computer is governed by instructions. To perform a task, an appropriate program consisting of a list of instructions is stored in the memory. So, this is something we know, that our program consists of a list of instructions, and these individual instructions are brought from the memory into the processor, which executes the specified operations. So, we have also looked at this, how the instruction gets executed. Data to be used as operands are also stored in the memory. So, the memory consists of both instructions and the data, and the instruction execution takes place in multiple steps. We have looked at these steps, and then we always have a simple data path or a control path to understand the instruction execution. That is, we have looked at a simple data path or a control path, using which we have understood how the instruction gets executed. Right. So, this is what we have looked at so far. So, what is it that we are going to look at in today's lecture? So, in today's lecture, we will look at how is performance measured and how is performance evaluated. So, that is what we are going to look at in today's lecture. So, if we look at the performance measures that we talk about, there are two performance measures that are important with respect to computer systems. So, one is response time and the other is throughput. Okay. So, response time and throughput are two terms that you would have come across with respect to computer systems in many other subjects that you have studied. Now, we will look at what is meant by response time and what is meant by throughput. Response time basically talks about how long it takes to do a task. So, this is very important for us. Response time is how long it takes to do a task, and throughput is the total work done per unit time. Remember, these are two parameters that we come across in many subjects, and it's important to understand this correctly. So, response time in general talks about how long it takes to do a task, and throughput talks about the total work done per unit time. So, if you're looking at tasks, we say how many of, for example, we say number of tasks done per unit time, per hour or per minute or per second, or we say number of transactions per second, or we talk about number of jobs performed per second or per hour. So, this is what we mean by throughput. Response time is the time, the total time, how long it takes to do a particular task. So, with respect to computer architecture, the questions that we would be interested in answering are, how are these response time and throughput affected by replacing the processor, say, with a faster version or adding more processors? So, what are these factors which are going to affect the response time and throughput? That is, how does the computer design affect the response time and throughput? This is what we need to understand. Right now, what we will do is, we will focus on response time and try to understand how the performance of a CPU can be measured. So, let us try to first define performance. So, what do we mean by performance? With respect to processors, we can look at it as 1 over execution time. So, what do I mean by this? We say that performance is inversely proportional to the execution time. That is, if my execution time is large, then I say that my performance is less. But if my execution time is small, that is, the job is getting done faster, then I know that the performance is better. So, in general, we say performance is inversely proportional to the execution time. So, if I am able to measure execution time accurately, I can measure the performance accurately, or I can say how good my performance is. So, if I say that X is n times faster than Y, a processor X or a machine X, let us say, is n times faster than Y, what do I mean by that? I am basically trying to take a ratio of the performance of X with respect to the performance of Y. So, which would in this case become execution time of Y divided by execution time of X. Okay, we call this, say, by a value n. So, this value n is what we mean when we say that X is n times faster than Y. So, execution time of Y divided by execution time of X will give you the value by which it is faster, which is normally referred to as speed up. We will come to that a little later. Okay. So, in general, because we have looked at performance as 1 over execution time, remember that when you say performance of X divided by performance of Y, you will get it as execution time of Y divided by execution time of X. Right. So, that will give you the improvement in performance of Y with respect to X. So, let us take an example here. So, let us say time taken to run a program, some program on a machine A is 10 seconds. Okay, and on a machine B, let us say it is 15 seconds. So, now if you are looking at comparing the performance of these two machines, so we say that execution time of B divided by execution time of A, what would that be? That is 15 seconds by 10 seconds. So, it is 1.5. Okay, so we say that A is 1.5 times faster than B. Okay, so this is what we mean by comparing performance. So, you can see that you are basically comparing performance here in terms of how the execution times, right, and saying that one machine is faster than another machine by a factor of 1.5. Okay. So, now this relative performance that we are talking about, it is comparing two different machines, is referred to by another performance measure called speed up. So, let us look at what is this speed up. Okay. So, speed up is looked at as execution time of machine B divided by execution time of machine A in this case, or in general, if I want to compare an old machine with a new machine, in general my speed up would be execution time old divided by execution time new. Okay. So, this is, remember again, execution time old comes in the numerator, execution time new will come in the denominator. And given that my execution time new would be lesser than execution time old, my speed up value will be greater than 1. In this previous example that we saw, for instance, speed up in this previous, we got a speed up of 1.5. 1.5 speed up we got because one machine was faster than the other by that particular factor. So, this speed up essentially tells you the factor by which a machine is faster than another. So, obviously, we know that if the speed up value is greater than 1, it is faster. If the speed up value turns out to be less than 1, that means it is a slower machine. Okay? So, that is how we look at speed up. So, now next question that comes out is, now that we know that we can measure performance in terms of execution time, how do I measure this execution time? Okay? So, in a processor, how do I actually measure the execution time? So, here we look at two things here. One we call as the elapsed time and another called the CPU time. Okay? Now, what do I mean by elapsed time? Elapsed time in general is the total response time, that is including all aspects of processing. So that is, you will have instructions being executed on the processor, plus, which is the processing time as such, plus there will be some input output operations that take place, which will take up some time. There will be some operating system related overhead, which will also take up some time. There may also be some idle time that is there. So all these put together will give you the total elapsed time. Okay, this is what we talk about. So this is normally used to determine the system level performance. That is, as a system, when I look at it with the input output, with all the different units put together, when I look at the entire system's performance, then we look at the elapsed time as the execution time. But we are looking at the CPU design or trying to evaluate a CPU architecture. So then we look at just the CPU time. So what is the CPU time? It's the time spent processing a given job. Okay, so here we discount the IO time and other jobs shares, that we do not worry about other jobs being executed in a multiprocessing scenario or whatever. Okay, we are looking at only this particular job. For this job, what is the time spent processing that particular job? So we do not worry about the IO time and so on. So it only will comprise of the user CPU time and the system CPU time. Okay, for the user's program, whatever CPU time is being used, and for his program, whatever time is used by the system. Okay, user CPU time and system CPU time. Okay. So this is what we mean by the CPU time. So when we look at it from an architecture perspective and when you're looking at it from a processor perspective, so you're typically normally concerned with the CPU time as our main measure of performance. Okay. And different programs are affected differently by both the CPU and the system performance. So we need to understand how that happens. So let us take a look at how this CPU time normally is calculated. Now to understand this CPU time calculation, we need to understand that the entire processor is run using what we call as a CPU clock. Okay, so this clocking is something that we need to understand. Any processor or any digital hardware in general is governed by a constant rate clock. Okay, so we all know what is a clock. We've looked at it in our digital courses. So what is a clock? It's basically an alternating signal of high and low values, and it's a periodic signal. So we have what is defined as a clock period, and all information transfer or whatever that happens is normally controlled by this timing which is given by this clock. Okay, so we have the difference, the time that you have between the rising edge and the other rising edge normally is referred to as the clock period. Okay, and if you look at how this clock will be used to control things on a processor, so typically what you do is you would say that during one clock cycle a data transfer or a computation may take place. Next clock cycle another data transfer or computation may take place. Next clock cycle another one may take place, and so on. And it is in between these clock cycles that some updation of state or some latching of values, updation of states, writing of values, these things may take place in this. So we use the clock period to determine when certain actions will take place. Okay. Now why is this clock cycle important? Of course, it is the one that helps us to time various events. In addition to that, this frequency of this clock cycle, or there is a clock period or inverse of the clock period which gives us the clock frequency, that is what will tell you how fast things are taking place on the system. Okay. So what is the clock period? It is the duration of a clock cycle. So for example, if I say that the duration of a clock cycle is 250 picoseconds, 250 picoseconds is about 0.25 nanoseconds, or pico is 10 to the power of minus 12, so it's a 250 into 10 to the power of minus 12 seconds. 1 over the period will be the clock frequency, or we refer to it as the clock rate. So this will give us the number of cycles per second. So for instance, if I say 4 gigahertz, it means that I'm talking about 4000 megahertz or 4.0 into 10 power 9 gigahertz. Okay, this is just two examples of what we mean by clock frequency and clock. You must be familiar with these two terms, but this is just to remind ourselves of this. So we will take a short break now and come back and continue with the rest of the topic. Welcome back after the break. So we were just looking at how the performance can be measured. So we said performance is measured in terms of CPU time, and the CPU time we said is normally CPU operation in general we said is governed by the clock. Okay. So CPU time therefore can be measured in terms of the clock cycle time. Okay. So how do we measure that? So CPU time we say is measured as CPU clock cycles taken for a particular operations into the clock cycle time. So we just said that we will do certain operations with respect to clock. Therefore, with respect to the clock cycle time, we can measure the overall CPU time. So CPU time is in general given as CPU clock cycles taken for a particular operation into the clock cycle time. Okay. Or in other words, instead of cycle time, if you take the clock rate or the frequency, you can write it as CPU clock cycles divided by the clock rate. So now if you look at this, remember our performance can be improved. How do we improve performance? We know that performance is inversely proportional to the execution time or the CPU time. Therefore, if I want to improve performance, I have to reduce my CPU time. So if I have to reduce CPU time, my CPU time should be small. What do I need to do? My CPU clock cycles must be less, right? And CPU clock rate should be high. Or in other words, if you look at this equation here, if I want this number to be small, both these numbers should be small. Clock cycles must be less and the clock cycle time should also be small. So what does it mean? It means that performance can be improved by reducing the number of clock cycles or by increasing the clock rate. Okay, these are two things that we need to look at. So normally the hardware designer must be aware of the trade-off that you have between the clock rate and the clock cycle count. Typically what happens is that when you try to improve one, there is always, you need to worry about the effect of it on the other. So that is something that as a hardware designer we need to be aware of. So now that we have a way of measuring the CPU time, let's take an example and see how the time can be measured. So let's say for instance, I have a computer A which is running at a frequency of 2 gigahertz. Okay, so the clock frequency is 2 gigahertz and that and the CPU time that is taken by this is 10 seconds. Okay, so I've got one process. This process running on computer A, which has a frequency of 2 gigahertz clock, it takes up about 10 seconds. Now I want to design a new computer B. Okay, so this new computer B, my aim is that I want to have a 6-second CPU time. Earlier this machine was taking 10 second CPU time, now I want to make it as a 6-second CPU time. Now, so the question is, now how do I do it? Obviously it means that this is going at 10 second CPU, it was taken 10 seconds and it was working at 2 gigahertz clock. If I want it in 6 seconds, it means that I will have to increase my clock frequency. So if I can do it with a faster clock, but let me assume that it uses 1.2 times the clock cycles of A. That is, when I increase this, let me assume that this machine B will require 1.2 times the clock cycles of A. So in that case, how much faster must my computer B's clock be? Okay, this is what we want to find out. Okay, let's look at this. So clock rate of B will be equal to clock cycles of B divided by CPU time of B. Now how do I get this equation? Basically from the fact that CPU time is equal to, CPU time is equal to clock cycles divided by clock rate. Okay, so I can write it the other way around and say clock rate is equal to clock cycles divided by CPU time. This is for machine B. So this is equal to 1.2 times clock cycles of A, because we said that the machine B, the same program running on machine B takes up 1.2 times the clock cycles of A. So 1.2 into clock cycles of A divided by CPU time B. Now I want it to be over in 6 seconds, therefore this is 6 seconds. Now clock cycles of A, this is what we need to find out, right? How many clock cycles of A will be used up? That will be equal to CPU time of A into the clock rate of A. So now we know that CPU time on A was 10 seconds and clock rate A was 2 gigahertz. Therefore 10 seconds into 2 gigahertz, 20 into 10 to the power 9 clock cycles was the clock cycles of A. So now what will be the clock rate of B, therefore substituting this value back over here. So you get 1.2 into 20 into 10 power 9 divided by 6 seconds, which is 24 into 10 power 9 by 6 seconds, which comes to about 4 into 10 power 9 or 4 gigahertz. So we know that I need to use a clock cycle of 4 gigahertz in order to achieve a 6-second CPU time on computer B. Okay, so you can see that using this simple formula that we had, which relates the clock cycles, CPU time and the clock rate, you can figure out how a designer must choose a particular frequency for operation or whatever. Okay, that was the purpose of looking at this particular example. So let's look at how this clock cycles that we talked about are measured. So we said it's given in terms of clock cycles. So how do I actually get this clock cycles for a given set of instructions being executed on a system? Okay, so that is what we need to understand next. So here we introduce two new terms now, one called the instruction count and the other called the CPI. Okay, now CPI basically stands for cycles per instruction. Okay, so this instruction count is the number of instructions that are going to be executed. So now we can say that the clock cycles that we talked about is equal to instruction count into the cycles per instruction. Instruction count gives me the number of instructions, so that into the number of cycles that it takes per instruction will give me the clock cycles. So therefore, now I can say that my CPU time therefore now is equal to, we said clock cycles into clock cycle time, right? So now that will become instruction count into CPI into clock cycle time. Or in other words, I can write this as instruction count into CPI divided by the clock rate. Instead of clock cycle time, if I take clock rate, this will come in the denominator. Okay. So, we say that CPU time therefore is instruction count into CPI into clock cycle time, or instruction count into CPI divided by the clock rate. Now, these two forms of this equation which gives us the CPU time are very important with respect to understanding the performance of a processor. Okay. So, we always come back to this, so please remember this. CPU time is instruction count, or what we call as IC, into CPI, which is the clock cycles per instruction, and the clock cycle time. Product of these three terms gives us the CPU time. Okay. Okay. Now, what are the things which determine the instruction count, CPI, and the clock cycle time? The instruction count for a given program will be determined by the program itself, what that program is expected to do, and the instruction set architecture, that is, what are the instructions which are there in that particular processor which the program can make use of, and the compiler, because the compiler is the one which is going to take a high level program and convert it to the this assembly, to this instructions which are going to be used by on the processor. So, how well the compiler chooses the instructions is also important. So, determined by program, the instruction set architecture, and the compiler, and the average cycles per instruction. So, instruction count we have seen is determined by these factors. The average cycles per instruction is determined by the CPU hardware. That is, how many cycles does each instruction take? That depends on how I have designed my hardware. Okay, so that's important. Now, here what is important, what is even more important is, if different instructions have different CPI, then I will have to look at the average CPI for a given process, for a given instruction mix. What do I mean by instruction mix? A set of instructions which constitute a program. For a given instruction mix, there will be an average CPI. So, this average CPI is the one which I will have to use to calculate the CPI that I am talking about over here. So, here when I said CPI, clock cycles per instruction, we almost assumed that all instructions will take the same number of clock cycles. That need not be the case. Different instructions may take different amount of clock cycles to execute, in which case I will have to find out the average CPI value here. Okay, this is important. So, once I know the instruction count and the CPI, doing a performance calculations becomes easier. Okay, so let's take an example now, how the CPI is calculated and how we calculate the CPU time using that and determine how much one machine is faster than the other. Okay, so let's take this. I have a computer A which has got cycle time of 250 picoseconds and a CPI of 2.0. Now here I am assuming that it's a constant CPI. Computer B has a cycle time of 500 picoseconds but a CPI of 1.2. Okay, now we want to find out which is faster and by how much. Let's assume that they have the same ISA. Okay, which means that the instruction count of both the programs on both the machines is the same, and so there's the only difference in the CPI and the clock cycle time. So, CPU time A will be equal to instruction count into CPI of A into the clock cycle time of A. So, that will be equal to, say, let me say instruction count was I. So, I into CPI of A is 2.0 into 250 picoseconds. So, I into 500 picoseconds is my CPU time of A. Now, CPU time of B will be instruction count into CPI of B into clock cycle time of B. So, which will be I into 1.2. Remember, we have CPI of 1.2 for computer B. So, I into 1.2 into 500 picoseconds. So, this comes to I into 600 picoseconds. Okay. So, now if we look at these two, we know that A is faster because A is taking less amount of time, I into 500 picoseconds. So, now I can find out how much it is faster by, that is my speed up of B with respect to A. Right. So, CPU time of B divided by CPU time of A. We know that A is faster than B. So, I need to find out now the speed up of A with respect to B. So, I say CPU time of B divided by CPU time of A, which will be I into 600 picoseconds by I into 500 picoseconds. The I and I will cancel out. So, you get a value of 1.2. So, we know that now A is faster by this much. By how much? By 1.2. Okay. So, this is how we can use the instruction count and the CPIs to understand and compare performances of different systems. So, now let us look at this CPI calculation in a little bit more of detail, right. That is, we know when all instructions take the same number of clock cycles, we have no problem. So, this CPI calculation is very important. We need to pay attention to it when different instructions take different amounts of clock cycles. So, how do you calculate this average CPI in that case? That is what we need to look at now. Okay. So, if different instruction classes take different number of clock cycles, then we say that the clock cycles will be given by sum of I equals 1 to n, CPI of class I into instruction count I. That is, I will find out that, let me assume I have n different classes of instructions 1 to n. So, for each type I know that for each instruction type I will have a certain number of instruction count in a given program, and for that instruction, for that type I know a particular value of CPI, which I am calling as CPI I. Okay. So, CPI I into instruction count I will give me the number of clock cycles taken for one particular set of instructions. So, now this I varies from 1 to n because I have n different types of instructions. So, for type I know that this is the amount of clock cycles it will take. So, for putting it together now, for all the types of instructions, it will be for I equals 1 to n, what is the total number of clock cycles? So, clock cycles will be given by summation of CPI I into instruction count I summed over I from 1 to n. Okay. So, now this is the number of clock cycles. So, now I can look at how I calculate the weighted average CPI. So, now CPI is, what is CPI? It is clock cycles divided by instruction count. So, what are the clock cycles now? That is this sum, this value that I have here, sum of I equals 1 to n CPI into instruction count I divided by the instruction count. Now, so if I divide this instruction count here, look at what I get. I can rewrite this as sum of CPI I into instruction count I by instruction count, which can also be looked at as the relative frequency. So, my CPI therefore can be looked at as CPI of I into relative frequency, summation of that from 1 to n. So, this is what will be my average CPI that I am calculating. We will look at this with an example so that you understand it easily. Okay. So, let us take for instance 3 types of instructions, 3 classes of instructions for a given program. So, I am taking one program and I am taking a class A, class B and class C. So, CPI for the class A instruction is 1. So, this takes only 1 cycle for instruction of type A, 2 cycles for instruction of type B, 3 cycles for instruction of type C. Okay. So, for this, let me take a particular instruction count in sequence 1. A sequence 1 program, let us say, okay, takes 2 instructions, it has 2 instructions of type A, 1 instruction of type B and 2 instructions of type C. Okay. So, for this sequence, I am going to find out what is my instruction count and I am going to find out what is the average CPI. Okay. So, what is the instruction count here? Instruction count is 2 plus 1 plus 2, which is 5. There are altogether 5 instructions. Okay. So, the clock cycles that will take will be, these 2 will take 1 clock cycle, this will take 2 clock cycles, this will take 3 clock cycles. So, my clock cycles will be 2 into 1 plus 1 into 2 plus 2 into 3, which is 10. So, now what is the average CPI? The average CPI will be number of clock cycles divided by number of instructions. So, 10 by 5, 2 will be my average CPI for this instruction sequence. So, similarly, if I take another instruction sequence, okay, where I am having 4 instructions of type A, 1 instruction of type B and 1 instruction of type C. So, in this case, what will be my instruction count here? The instruction count here will be 4 plus 1 plus 1. So, this instruction count here is 6, and then the number of clock cycles that it takes will be 4 into 1 plus 2 into 1 plus 3 into 1. So, that will become 9. So, what will be the average CPI in this case? It will be number of clock cycles by the instruction count here, 9 divided by 6. So, you can see that the average CPI here will be 1.5. So, we can see that depending on the mix of instructions that we have, the average CPI will vary. That is because each instruction class is taking up different number of clock cycles. So, the average CPI will vary depending on the instruction mix that we have. So, that is important here. So, this instruction mix is the important factor that we need to consider. So, let us look at the same thing from an instruction frequency point of view. The same thing, right? So, what do we have here? The same CPI values I am using for the 3 classes of instructions A, B and C. Only thing is I have written now the same values in terms of the relative frequency. So, for instance, if you look at this previous thing here, we said that this is 2 out of altogether how much? 2 plus 1, 3 plus 2, 5. So, 2 out of 5 instructions are of type A. So, 2 by 5, that is about 40%. So, that is what I am mentioning over here. Okay. So, if you look at this here, I am talking about 40% of instructions are of type A, 20% of type B, 40% of type C. So, now my average CPI calculation, if I am given the relative frequency, becomes much easier because my average CPI is just calculated as 1 into 0.4, right, 1 into 40% plus 2, which is the CPI of class B, into 20% plus 3 into 40%, 3 into 0.4. So, 1 into 0.4 plus 2 into 0.2 plus 3 into 0.4, which is 2.0. the same CPI that we got in the previous case. Now in this, for the second example, similarly if you take, so let's say this was 66.66%, this was 16.67% and this 16.67%. So what will be the average CPI here? It will be 1 into 66.66 or percent, therefore 0.667. So 2 into 0.167 and 3 into 0.167, let's say. So this will come to about 1.5. So you will find that you can do the calculation either using the relative frequency or using the, okay. So that is what you will be able to do with this example. Do a quick recap of what we just looked at now. So the clock cycles we said is instruction count into cycles per instruction, which is given as instruction count into CPI into clock cycle time, or instruction count into CPI divided by the clock rate. And the CPU time is given as instructions per program into clock cycles per instruction into seconds per clock cycle. So overall, this instruction count is nothing but the instructions per program, CPI is the clock cycles per instruction, and the clock rate is the number of seconds per clock cycle. So this is what gives us our CPU time on the whole. So in this previous example that we looked at just now, I am just giving you a summary of the same thing again. So for the sequence 1, we got an IC of 5 and an average CPI of 2.0. Sequence 2, IC of 6 and an average CPI of 1.5. So now if you look at the CPU time of these two, compare the CPU time of these two, you can see that we get again using the same instructions per program into clock cycles per instruction into seconds per clock cycle, you will find that this takes 5 into 2.0 into 10 nanoseconds, 100 nanoseconds. And for sequence 2, it takes up 6 instructions into 1.5 is the instruction count, and 10 nanoseconds is my clock cycle time. So it takes up 90 nanoseconds. So we can see that for the sequence 1 and sequence 2, same CPU, this will take up 100 nanoseconds and this takes up 90 nanoseconds. So we can see that even though the number of instructions is larger here, the average CPI is less and therefore it takes up a lesser amount of time. So this kind of an analysis, this kind of understanding is useful for us to understand how an instruction execution time influences the actual time taken for execution. Okay. So it is using these kind of parameters that we are able to understand the performance of a system. Okay. So now that we know how to measure the performance, how is it that in general the different processes are compared? Okay. To understand this, what we need to understand is that there is something called benchmarks which are used. So what are benchmarks? They are some standard programs that are used for comparison. Okay. So normally there we have a standard called the Standard Performance Evaluation Corporation. This is actually a consortium of different industries which comes up with this particular standard. So this these people, they develop benchmarks for various operations, for CPU, IO, web operations and so on. Okay. And what is normally done here is you calculate the execution time of various programs which are there in this benchmark, and you take an average of those values in order to identify the actual performance of a machine. Okay. So normally what they also do here is they will take this execution time ratio, which is the speed up that we have talked about with respect to some standard machine, and then they will take the geometric mean of the performance ratios and find out that as one parameter which is used to compare various machines. So this is more in terms of practically how things are done. And then once you have something like this, this basically gives you a big comparison that is normally done of different architecture, say the Optron machine that is for instance that is used. So this is an example of how a geometric mean would be calculated. You will have different programs for which the instruction count, the CPI, the execution time and all these things will be calculated. And then you will find the spec ratio, how fast this program is with respect to a previous standard version. And then the geometric mean of all these will be taken as one spec value, using which you will be able to compare the performances of different machines. So like this we have calculated for one machine. Similarly, you will calculate for another machine and then you compare the spec ratios, and that will tell you how much faster one machine is than the other. Okay. So this is to give you an overview of what is important in terms of performance and in terms of how this performance is normally measured. So that is what we have looked at now. Performance measure, CPU time, how it is calculated, and some examples of calculating the CPU time. Okay. So now time for some questions to understand what we have looked at today. So what is question number 1? What is meant by response time? Question number 2, what is throughput? Question number 3, how is the execution time of a processor determined? Question number 4, what is meant by speed up? Question number 5, give the equation to calculate CPU time. Question number 6, will two CPUs having the same IC, instruction count and frequency, but different instructions have the same CPU time? Why or why not? So these are questions that should help you to understand what you've learned today. Thank you.